Welcome back to our course on memory device technology for AI/ML computing. I'm your instructor, Dr. Shubhadi from IIT Hyderabad. So let's try to recall what we were discussing the last time around. Last time around, we had a brief historical perspective regarding the NAND flash. Then we started looking at some transistor basics to understand how the flash cell operates. And what we figured out, this is where we stopped last time, what we figured out is the way to convert a 1T transistor from a logic device to a storage device or a memory storage device is to be able to effectively tune the threshold voltage of the transistor. And we saw as an example the best way to probably play dynamically with the threshold voltage of the transistor is to introduce trap charges into the oxide of the of the transistor. Like we saw last time, if the trap charges is zero, or in an ideal case, the threshold voltage of the transistor is such that it is much lesser than the decided reference voltage. And if you have negative trap charges, it so happens that there has to be an extra gate voltage that needs to be applied to overcome the accumulation of surface charges which were induced because of the negative trap charges. And then you come to flat band voltage, and only after that you can reach the condition of having the surface completely inverted. That means that the number of surface electrons at the oxide and semiconductor interface will be equal to the number of carriers, p-type carriers at the bulk, right? And this is reflected by a higher threshold voltage as indicated by the red curve. So if you have a predefined reference voltage on the gate axis, gate voltage axis, the transistor without any trap charges will be at an on state at the given reference voltage, and for the one where there are negative trap charges, the transistor will be in the off state. And by reliably being able to introduce trap charges and removing trap charges, you will be able to transform a transistor device into a memory device. So today we will begin our study where we left last time. We will see how such kind of introduction of trap charges and removal of trap charges is facilitated in a transistor, and as we know, that is done by modifying the gate stack of the transistor. So from a normal transistor which has just a oxide layer and a metal layer, we have now transformed that into a flash cell which will behave like a storage element. So what does the gate stack of the flash cell look like? It is a little more involved entity which has four functional parts. The first is the tunnel oxide, which is also known as TO. The second is the charge storage layer, which is marked in green color. And this, as we will see, is the most important functional layer, because this is where the introduced charges from the channel will be introduced and pulled in and pulled out of. Okay. The next is the blocking oxide or BO, and the final is the control gate or CG. Okay. So let us now do a little bit of deep dive into what the functionality of these four layers are. So let us begin with the tunnel oxide. The job of the tunnel oxide is very simple. It is to facilitate a very controlled exchange of electrons to and from the channel. To and from the channel to what? To this charge storage layer. So what we understand from this is that this tunnel oxide is actually the interface which controls how charges are pulled in from the channel and then pushed back into the channel from the charge storage layer. Now, as the name suggests, the charge transport mechanism is through quantum mechanical tunneling, and we will see more about that later. The second, as we said, is the most important functional layer. This is the storage layer where charges are stored and removed from, and that is indicated in this green schematic, green color in this particular schematic. And this charge storage layer, whether there are electrons in the charge storage layer or not, finally decides what will be the effective threshold voltage of the transistor. So this is where the trap charges will be stored, and that will govern what is the threshold voltage of the transistor. The next is the blocking oxide. As the name suggests, the blocking oxide is slightly thicker oxide, slightly thicker compared to the tunnel oxide. And the objective of the blocking oxide is that whatever are the charges that are stored in the charge storage layer do not escape from the control gate. They should not escape from the control gate. They should only interact the charges which are put inside the storage layer or extracted from the storage layer. The only interaction direction is from the channel, not from the control gate. And finally, the control gate is the one which will be connected to the word line of your array, and this control gate determines what will be the different operating mechanisms. That means whether the voltage on the control gate will finally determine whether charges will be injected into the charge storage layer or out of the charge storage layer. So it facilitates the overall operation of the flash cell. With this understanding, it would be very important to note that there are two different kinds of flash cells, two different flavors of flash cells, depending on what this charge storage layer, which is the most important functional layer, is based out of. What is the material that constitutes the charge storage layer basically classifies the flash cell into two different entities. So these are popularly known as the floating gate flash cell or the charge trapping flash cell. And as I said, the key difference is what is the constitution of the charge storage layer. For the floating gate cell, the charge storage layer constitutes primarily of a metal. So this green entity in the case of floating gate is a metal. Most generally, it is very heavily doped polysilicon. As you may know, even in previous generations of transistors, the gate metal was not actually a metal, which is the case in new generations of transistors, but a heavily doped polysilicon. And due to different reasons, which we will not get into, they are eventually changed into into aluminum or some kind of different metal. But for floating gate transistors, the charge storage layer is generally heavily doped polysilicon. Whereas for the charge trapping flash cell, the charge storage layer constitutes not of a metal but that of an insulator. Now this insulator is also a specially designed insulator. Generally it is silicon nitride. Why is it silicon nitride? Because it is said that silicon nitride has reasonable amount of band gap and reasonable amount of defects to be able to trap electrons into its defect levels, which are there within the band gap. So as we will see, when we go from 2D to 3D flash, we will see that how the floating gate is more useful. It's a simpler implementation, but it becomes very difficult to scale the floating gate flash cell. So that is why we start moving towards the charge trapping flash cell. The next important difference is what are the thicknesses and quality of tunnel oxide or the material of the tunneling and the blocking oxide in the floating gate and the charge trap cell. Whereas the tunnel oxide for floating gate transistors or floating gate flash cell is 9 nanometers of SiO2, roughly 9 nanometers. Because charge trapping is a newer generation, you have also tried to scale down the thickness of your tunneling oxide to 4 to 5 nanometers. But more importantly is the difference between the blocking oxide of the floating gate and the charge trapping cell. Remember, the job of the blocking oxide was to ensure that there is no escape of the charges which are trapped in the charge storage layer from the control gate. So since in the previous generation of floating gate transistor, the charge storage layer was essentially metallic or heavily doped polysilicon, there was a chance that there could be some migration of charges into the charge gate through the blocking oxide. Therefore, a more finely designed blocking oxide, which involved a heterostructure of SiO2, silicon nitride, and SiO2, also known as oxide ONO, oxide nitride oxide heterostructure, was used as the blocking layer. That was roughly 15 nanometers thick. This is because this silicon nitride improved the gate capacitance. Why? Because silicon nitride has higher permittivity as compared to SiO2. So because you are going to higher thicknesses to ensure blocking, the silicon nitride gave you a little bit more higher gate control. And also, if there are any stray charges that somehow manage to leak out from the charge storage layer, the job of the silicon nitride layer in the blocking oxide was also try to kind of capture them and store them. Okay, so that it doesn't escape from the control gate. However, since in charge trapping flash cells, that is not really a constraint because the insulator itself is a silicon nitride layer. Such important considerations are not required, and therefore just an 8 nanometer of SiO2 itself can serve as a good barrier layer. Okay, so this ONO blocking oxide is not always needed. And as I have been discussing, the use case for floating gate transistor was for the first generation of flash cells from 1980s, late 1980s to mid 2010s, and that is what is used for the 2D NAND flash and also for NOR flash. And when we study 3D NAND flash, which is a very highly scaled modern day version of your flash cell and which has actually revolutionized how we do storage, we will realize that it becomes very difficult to scale the floating gate transistor because the charge storage layer is a metallic counterpart, and therefore we move for the new generation from the floating gate transistor to charge trapping transistor. So this charge trapping transistor is a much more evolved and scaled version of the floating gate transistor, and that is what is primarily being used for highly scaled 3D NAND flash memory. Okay, so next what we will get into is, with this understanding, it will be enough to have a more qualitative feel for what are the different operation mechanisms that are happening in the flash cell. So the first important operation mechanism is called the program operation. So what happens in the program operation? As I will show you in this animation, in the program operation, let me show you again. In the program operation, what is happening is electrons which were earlier residing in the channel region is pulled in through the tunnel oxide, or more technically correct, will tunnel through the tunnel oxide and go and sit in the charge storage layer. So this is the program operation, and by the virtue of that, since now you have pulled in electrons into the charge storage layers, the trap voltage or the trap concentration is negative trap concentration. Therefore, the threshold voltage of the transistor will of course shift on the right hand side, or this kind of structure where there are negative Q trap will have higher threshold voltage, by the virtue that now the gate voltage which will be applied at the control gate has to work harder to eliminate the accumulated positive charges first and then invert the channel. This is something that we have discussed in detail in the previous class. Whereas the second operation is exactly the opposite, and this is what the animation is telling us. In the second operation, what happens, as you can see from the animation, is the erase operation. And in the erase operation, negatively charged electrons are pushed out of are pushed out of the charge storage layer into the channel region. Okay, and they become free carriers. So in program, free carriers which are present in the channel are made trapped carriers inside the charge storage layer, whereas in the erase operation, trapped charges inside the floating gate layer or the charge storage layers are pushed out and made free carriers in the channel region. Okay, and as a result, the threshold voltage of a flash transistor or flash cell which has undergone an erase operation will be, of course, much lesser as compared to that in the program operation, by the virtue that it will behave more like an ideal cell with no trapped charges. Okay, since these are not two different structures but operations which are happening in the same structure, it may be worthwhile to indicate both of them into the same to integrate them in the same schematic. So as you can see from the from your animation, all that is happening in the flash cell is this repeated trapping and detrapping of negatively charged electrons to and fro for the charge trapping layer. Okay, and this is what changes the threshold voltage from erase operation to program operation, and these repeated cycling from program operation and erase operation is what is the main operating mechanism of your charge of your flash cell. And as we have already studied that how do you do the read? You basically select a gate voltage which is between the threshold voltage of the erase operation and the program operation. When it is in erase state, the transistor is in on state. You see a finite current at the reference voltage or read voltage, and at the same read voltage in the program state, it is in off state. Okay, so as a result, what can happen is the same transistor, by the virtue of charges being trapped and detrapped, can behave like a memory device, or in this specific case, more like a storage device. Why does it behave like a storage device? What is the meaning of a storage device? That means it has non-volatile operation. The meaning of non-volatile operation is that once these charges are trapped into the charge storage layer, until you actively do something at the control gate, they will not get detrapped. So as long as you don't do a erase operation, they will be the electrons will be trapped in the charge storage layer, right? And this will stay for a very, very, very long time until you do the erase operation. So this is the meaning that it is behaving like a storage device. And the next important question that we will start obviously asking is, what are the biasing conditions? What are the voltages that you need to apply at the control gate, at the source and drain terminals, and even at the substrate to facilitate the program operation and the erase operation? And if you think very carefully, the biasing mechanism for programming and erase is very simple at the cell level. Why is this the case? Because in the program operation, all you need to do is pull negative charges into the floating gate. So it is obvious that in program operation, you have to apply a large positive bias at the control gate terminal, and vice versa for the erase operation. But the cell biasing may look very intuitive, but the array biasing is very, very complicated, very involved, and to study both of them together would be very valuable. But before we get into that, we should have a very quick understanding of what the different array architectures are. In the next class, we will start looking at what are the different array organizations. So let us conclude our study today. We saw today how program and erase operations happen by specially designed floating gate transistor with a charge storage layer. Program and erase operation happen when you try to pull electrons into the the charge storage layer and you try to push them out back into the channel. Thank you very much. Let's meet for the next class.